Here's the big idea for Chapter 2. An object in mechanical equilibrium is stable without changes in motion. Things that are in balance with one another illustrate equilibrium. Things in mechanical equilibrium are stable without changes of motion. The rocks are in mechanical equilibrium. An unbalanced external force would be needed to change their resting state. Section 2.1. A force is needed to change an object's state of motion. A force is a push or a pull. A force of some kind is always required to change the state of motion of an object. The combination of all forces acting on an object is called the net force. The net force on an object changes its motion. The scientific unit of force is the Newton, abbreviated capital N. The net force depends on the magnitudes and directions of the applied forces. Let's look at the three scenarios here to demonstrate that. In the first scenario, a 5 Newton force is applied to the right, along with a 10 Newton force, yielding a net force of 15 newtons. In the next scenario, a 5 Newton force is applied to the left, a 10 Newton force is applied to the right, yielding a net force of 5 newtons to the right. In the third scenario, a 5 Newton force is applied to the left, a 5 Newton force is applied to the right, yielding a net force of 0 newtons. There's no net force on the object. When the girl holds the rock with as much force upward as gravity pulls downward, the net force on the rock is 0. A stretch spring is under a stretching force called tension. This tension can be measured in pounds or newtons. Pounds and newtons are units of weight, which are units of force. Units of force. The old unit is pounds, abbreviated with an lbs. The SI unit for force is a newton, abbreviated with a capital N. 1 newton equals 0.22 pounds. With nothing on the hook, the scale reads 0 pounds or 0 newtons. There is no tension. The upward tension in the string has the same magnitude as the weight of the bag, so the net force on the bag is 0. The bag of sugar is attracted to Earth with a gravitational force of 2 pounds or 9 newtons. There are two forces acting on the bag of sugar: a tension force acting upward and weight acting downward. The two forces on the bag are equal and opposite. The net force on the bag is 0, so it remains at rest. A vector is an arrow that represents the magnitude and direction of a quantity. A vector quantity needs both magnitude and direction for a complete description. Force is an example of a vector quantity. A scalar quantity can be described by magnitude only and has no direction. Time, area, and volume are scalar quantities. The vector represents a velocity of 60 kilometers an hour to the right. It's comprised of 3 segments, 1 centimeter long, each centimeter equaling 20 kilometers per hour. Scalars act like ordinary numbers, but with vector quantities, direction matters. How can you change an object's state of motion? A force is needed to change an object's state of motion. Section 2.2, Mechanical Equilibrium. You can express the equilibrium rule mathematically as sigma F equals 0. Mechanical equilibrium is a state where no physical changes occur. Whenever the net force on an object is 0, the object is in mechanical equilibrium. This is known as the equilibrium rule. The Greek sigma symbol stands for the sum of. F stands for forces. For a suspended object at rest, the forces acting upward on the object must be balanced by other forces acting downward. In this case, the ball was suspended by a force from the table, pushing it upward against the pull of the Earth's gravitational force. The vector sum equals 0. The sum of the upward vectors equals the sum of the downward vectors. Sigma F equals 0, and the scaffold is in equilibrium. Here are the downward forces, the weights of the men and the scaffold. And here are the upward forces added, the tensions in the ropes. The sum of all the forces is 0, so the men and the scaffold are in mechanical equilibrium. If the gymnast hangs with her weight evenly divided between the 2 rings, how would scale readings in both supporting rods compare with her weight? Suppose she hangs with slightly more of her weight supported by the left ring. How would a scale on the right read? The answer? In the first case, the reading on each scale will be half her weight. In the second case, with more of her weight is supported by the left ring, the reading on the right reduces to less than half her weight. The sum of the scale readings always equals her weight. How can you express the equilibrium rule mathematically? You can express the equilibrium rule mathematically as sigma F equals 0. Section 2.3, support force. For an object that rests on a horizontal surface, the support force must equal the object's weight. What forces act on a book lying at rest on a table? One is the force due to gravity, the weight of the book. There must be another force acting on it to produce a net force of 0, an upward force, opposite to the force of gravity. The upward force that balances the weight of an object on a surface is called the support force. A support force is often called the normal force. The table pushes up on the book with as much force as the downward weight of the book. The table supports the book with a support force, the upward force that balances the weight of an object on a surface. The upward support force is positive and the downward weight is negative. The two forces add mathematically to 0. Another way to say the net force on the book is 0 is sigma F equals 0, or the sum of all forces equals 0. The book lying on the table compresses atoms in the table and they squeeze upward on the book. The compressed atoms produce the support force. The upward support force, in this case, is as much as the downward pull of gravity. The foot is standing on a scale. What is the net force on a bathroom scale when a 110-pound person stands on it? Answer: 0. The scale is at rest. The scale reads the support force, not the net force. Suppose you stand on 2 bathroom scales with your weight evenly distributed between the 2 scales. What is the reading on each of the scales? What happens when you stand with more of your weight on one foot than the other? In the first case, the reading on each scale is half your weight. In the second case, if you lean more on one scale than the other, more than half your weight will be read on that scale, but less than half on the other. The total support force adds up to your weight. For an object that rests on a horizontal surface, what is the support force equal to? For an object that rests on a horizontal surface, the support force must be equal to the object's weight. Section 2.4, equilibrium for moving objects. Objects at rest are said to be in static equilibrium. Objects moving at constant speed in a straight line path are said to be in dynamic equilibrium. The state of rest is only one form of equilibrium. An object moving at constant speed in a straight line path is also in a state of equilibrium. Once in motion, if there is no net force to change the state of motion, it is in equilibrium. An object under the influence of only one force cannot be equilibrium. Only when there is no force at all, or when 2 or more forces combine to 0, can an object be in equilibrium. This rocket ship is in outer space, so there should be very little gravity acting on it. So the only force on the object is the propulsion from the engine. When the push on the desk is the same as the force of friction between the desk and the floor, the net force is 0 and the desk slides at an unchanging speed. If the desk moves steadily at constant speed without a change in its motion, it is in equilibrium. Friction is a contact force between objects that slide or tend to slide against each other. In this case, the sum of all forces equals 0, meaning that the force of friction is equal in magnitude and opposite in direction to the pushing force. An airplane flies horizontally at constant speed in a straight line direction. Its state of motion is unchanging. In other words, it is in equilibrium. 2 horizontal forces act on the plane. One is the thrust of the propeller that pulls it forward. The other is the force of air resistance, air friction, that acts in the opposite direction. Which force is greater? Neither, for both forces have the same strength. Call the thrust positive, then the air resistance is negative. Since the plane is in equilibrium, the 2 forces combine to equal 0. How are static and dynamic equilibrium different? Objects at rest are said to be in static equilibrium. Objects moving at constant speed in a straight line path are said to be in dynamic equilibrium. Section 2.5, Vectors. To find the resultant of 2 vectors, construct a parallelogram wherein the 2 vectors are adjacent sides. The diagonal of the parallelogram shows the resultant. The sum of 2 or more vectors is called their resultant. Combining vectors is quite simple when they are parallel. If they are in the same direction, they add. If they are in opposite directions, they subtract. The tension in the rope is 300 newtons, equal to Nellie's weight. The tension in each rope is now 150 newtons, half of Nellie's weight. In each case, the sum of all forces is equal to 0. The parallelogram rule. To find the resultant of non-parallel vectors, we use the parallelogram rule. Consider two vectors at right angles to each other, as shown below. The constructed parallelogram in this case is a rectangle. The diagonal is the resultant, r. In the special case of two perpendicular vectors that are equal in magnitude, the parallelogram is a square. The resultant is the square root of 2 times one of the vectors. For example, the resultant of two equal vectors of magnitude 100 acting at a right angle to each other is 141.4. When Nellie is suspended at rest from the two non-vertical ropes, is the rope tension greater or less than the tension in two vertical ropes? You need to use a parallelogram rule to determine the tension. Notice how the tension vectors form a parallelogram in which the resultant r is vertical. Nellie's weight is shown by the downward vertical vector. An equal and opposite vector is needed for equilibrium, shown by the dash vector. Note that the dash vector is the diagonal of the parallelogram defined by the dotted lines. Using the parallelogram rule, we find that the tension in each rope is more than half her weight. As the angle between the ropes increases, tension increases, so that the resultant, the dash line vector, remains at 300 newtons upward, which is required to support the 300 Newton Nellie. When the ropes supporting Nellie are at different angles to the vertical, the tensions in the two ropes are unequal. By the parallelogram rule, we see that the right rope bears most of the load and has the greater tension. You can safely hang from a clothesline hanging vertically, but you will break the clothesline if it is strung horizontally. Two sets of swings are shown at right. If the children on the swings are of equal weights, the ropes of which swing are more likely to break? Answer. The tension is greater in the ropes hanging at an angle. The angled ropes are more likely to break than the vertical ropes. Consider what would happen if you suspended a 10 Newton object midway along a very tight, horizontally stretched guitar string. Is it possible for the string to remain horizontal without a slight sag at the point of suspension? No way. If the 10 Newton load is to hang in equilibrium, there must be a supporting 10 Newton upward resultant. The tension in each half of the guitar string must form a parallelogram with a vertically upward 10 Newton resultant. How can you find the resultant of two vectors? To find the resultant of two vectors, construct a parallelogram wherein the two vectors are adjacent sides. The diagonal of the parallelogram shows the resultant.